In number theory and combinatorics, a partition of a positive integer n, also called an integer partition, is a way of writing n as a sum of positive integers. Two sums that differ only in the order of their summands are considered the same partition. For example, 4 can be partitioned in 5 distinct ways: 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. The order-dependent composition 1 plus 3 is the same partition as 3 plus 1, while 1 plus 2 plus 1 and 1 plus 1 plus 2 are the same partition as 2 plus 1 plus 1. A summand in a partition is also called a part. The number of partitions of n is given by the partition function p, n. So p, 4, equals 5. The notation I*cent n means that I is a partition of n. Partitions can be graphically visualized with Young diagrams or Ferrers diagrams. They occur in a number of branches of mathematics and physics, including the study of symmetric polynomials, the symmetric group and in-group representation theory in general. Examples: the 7 partitions of 5 are 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1. In some sources, partitions are treated as the sequence of summands, rather than as an expression with plus signs. For example, the partition 2 plus 2 plus 1 might instead be written as the tuple, or in the even more compact form where the superscript indicates the number of repetitions of a term. Representations of partitions: there are two common diagrammatic methods to represent partitions, as Ferrers diagrams, named after Norman MacLeod Ferrers, and as Young diagrams, named after the British mathematician Alfred Young. Both have several possible conventions. Here, we use English notation, with diagrams aligned in the upper left corner. Ferrers diagram equals, the partition 6 plus 4 plus 3 plus 1 of the positive number 14 can be represented by the following diagram. The 14 circles are lined up in 4 rows, each having the size of a part of the partition. The diagrams for the 5 partitions of the number 4 are listed below. Young diagram equals. An alternative visual representation of an integer partition is its Young diagram. Rather than representing a partition with dots, as in the Ferrers diagram, the Young diagram uses boxes or squares. Thus, the Young diagram for the partition 5 plus 4 plus 1 is, while the Ferrers diagram for the same partition is. While this seemingly trivial variation doesn't appear worthy of separate mention, Young diagrams turn out to be extremely useful in the study of symmetric functions and group representation theory. In particular, filling the boxes of Young diagrams with numbers obeying various rules leads to a family of objects called Young tableaus, and these tableaus have combinatorial and representation theoretic significance. As a type of shape made by adjacent squares joined together, Young diagrams are a special kind of polyomino. Partition function: in number theory, the partition function p, n, represents the number of possible partitions of a natural number n, which is to say the number of distinct ways of representing n as a sum of natural numbers. By convention p, 0, equals 1, p, n, equals 0 for n negative. The first few values of the partition function are equals 1, 1, 1, 2, 3, 5, 7, 11, 15, 22, 30, 42, 56, 77, 101, 135, 176, 231, 297, 385, 490, 627, 792, 1002, 1255, 1575, 1958, 2436, 3010, 3718, 4565, 5604, €. The value of p, n, has been computed for large values of n, for example p, 100, equals 190,569,292, p, 1000, is 2406146786403262247 692,149,727,991 or approximately 2.40615 A, 1031, and p. 10,000, is 36,167,251,325. 906,916,435,144, or approximately 3.61673 A, 10,106. As of June 2013, the largest known prime number that counts a number of partitions is p. 120,052,058, with 12,198 decimal digits. Generating function equals, the generating function for p, n, is given by expanding each factor on the right-hand side as a geometric series. We can rewrite it as 1 plus x2 plus x3 plus 1 plus x2 plus x4 plus x6 plus 1 plus x3 plus x6 plus x9 plus. The xn term in this product counts the number of ways to write n equals a1 plus 2a2 plus 3a3 plus equals plus plus plus, where each number I appears I times. This is precisely the definition of a partition of n, so our product is the desired generating function. More generally, the generating function for the partitions of n into numbers from a set A can be found by taking only those terms in the product where k is an element of A. This result is due to Euler. The formulation of Euler's generating function is a special case of a Q-proclammer symbol and is similar to the product formulation of many modular forms, and specifically the Dedekind eta function. The denominator of the product is Euler's function and can be written, by the pentagonal number theorem, as where the exponents of x on the right-hand side are the generalized pentagonal numbers. That is, numbers of the form 1/2 m, 3ma1, where m is an integer. The signs in the summation alternate as. This theorem can be used to derive a recurrence for the partition function, p, k, equals p, ka1, plus p, ka2, ap, ka5, ap, ka7, plus p, ka12, plus p, ka15, ap, ka22, a. Where p, 0, is taken to equal 1, and p, k, is taken to be 0 for negative k. Congruences equals. Srinivasa Ramanujan is credited with discovering that congruences in the number of partitions exist for arguments that are integers ending in 4 and 9. For instance, the number of partitions for the integer 4 is 5. For the integer 9, the number of partitions is 30. For 14 there are 135 partitions. This is implied by an identity, also by Ramanujan, where the series is defined as. He also discovered congruences related to 7 and 11. And for p equals 7 proved the identity. Since 5, 7 and 11 are consecutive primes, one might think that there would be such a congruence for the next prime 13, for some a. This is, however, false. It can also be shown that there is no congruence of the form for any prime b other than 5, 7, or 11. In the 1960s, A.O.L. Atkin of the University of Illinois at Chicago discovered additional congruences for small prime moduli. For example, Ono proved that there are such congruences for every prime modulus. Later, Ahlgren and Ono showed there are partition congruences modulo every integer k' to 6. Partition function formulas equals. Recurrence formula. Leonhard Euler's pentagonal number theorem implies the identity. Where the numbers 1, 2, 5, 7 that appear on the right side of the equation are the generalized pentagonal numbers for non-zero integers k. More formally, where the summation is overall non-zero integers k and p, m, is taken to be 0 if mn then p, n, m, equals p, n, n, equals p, n. Then, to compute p, 7, the above list leads to the following, where the indented list items represent the count of the number of items in that grouping, 7, p, 0, 6, p, 1, 5, p, 2, 4, p, 3, 3, p, 4, 3, 2, p, 5, 2, 1, p, 6, 1. This arrangement illustrates the recursive nature of this function. Given the above is intuition, here is a Java program which computes p, n. This algorithm is suitable for n,